Hello student to the Foundation of Classical Electrodynamics course. Under module 2, today we will going to discuss more about the electrostatic potential. So, today we have, this is class number 28. And let us first write what we get in the last class. So, we know that divergence of the electric field is rho by epsilon 0 and curl of E is 0. These two information leads to the formation of the potential energy exploiting the Helmholtz theorem, and last year we did it. We find that electric field can be represented in terms of a scalar field phi, which is the electrostatic potential, and phi can be written in terms of this, because this is the precisely the Helmholtz theorem, and that is 1 by 4 pi epsilon 0 integration of rho, then r prime r minus r prime and dv prime over v prime. So, I can find, and also the vector potential for the vector potential for the electric field E is simply 0. Okay, we do not have any vector potential, but the scalar potential is very much there. And the scalar potential is defined by phi, which is this quantity. Okay, from Coulomb's law we try to understand this. From Coulomb's law I can write it. So, from Coulomb's law now today we are going to understand the expression of the scalar potential. Because the Coulomb's law gives us the electric field, the expression of the electric field. So, if I take the divergence, if I take the gradient of that, if I write this electric field in terms of a scalar potential in this way, then I can extract the information of the scalar potential. So, let us try to do that. So, my electric field I can write here in this way, which is 1 by 4 pi epsilon 0 and then integration rho r prime r minus r prime cube and r minus r prime vector and dv prime. This is the electric field due to the charge distribution rho at some point. So, if we have a charge distribution here, so this is the charge distribution, and from a given coordinate system, this is r prime, this is r, and this is r minus r prime. So, the field I am calculating at this point, and this is the charge distribution we are having. So, this is the structure. For that, electric field should be this one. I need to integrate. So, rho is here, which is a function of r prime, and I can calculate the volume integral with this, and then the total electric field I can calculate. Well, I can rewrite this expression in a slightly different way by exploiting the fact that minus of divergence of this quantity, which is 1 divided by mod of r minus r prime, is simply r minus r prime divided by r minus r prime cube. So, that we know, and if you calculate then you will find this. I suggest you to please check by yourself that whether you are getting this or not. Very simple calculation. Now, I am going to use, I just replace r minus r prime divided by mod of r minus r prime cube with this value here in this equation, and if I do, my ER should be E function of r is simply minus of 1 by 4 pi epsilon 0 and then integration rho r prime, and this quantity I just replace the divergence of the gradient of 1 r minus r prime and dv prime. So, this quantity I can make this divergence outside, because it is this divergence is operating over r. So, I can take it outside with a negative sign, then it should be divergence of the entire term. Sorry, I can take this gradient, I am saying divergence, but this gradient outside. So, I will finally have this 1 by 4 pi epsilon 0, this volume integral rho r prime and then r minus r prime and dv prime. So, this quantity is nothing but phi. So, I can write it as minus of phi, and phi becomes this. Which we already find exploiting the Helmholtz theorem. So, this is the electrostatic scalar potential, or simply electrostatic potential. Electrostatic potential. Okay. So, the next thing is from the expression the next things is the Poisson's equation, very important. And that we can simply understand that divergence of E is equal to rho by epsilon 0, and also E can be written as minus of gradient of a scalar field phi, which is called the electrostatic potential. So, if I replace this in the first equation, then I simply have divergence of minus of gradient of the scalar field phi is rho by epsilon 0. This quantity, this is not new, we have already discussed this quantity earlier. This is simply forms, this simply forms the Laplacian, and which is del square. So, this basically leads to a del square operator, and I can write it as minus of rho by epsilon 0. So, this very equation is called the Poisson equation. Okay. Now, if rho is equal to 0, we are taking the, we are putting the condition that there is a region where the charge density vanishes or there is no charge density, then this equation is simplifies to this, and this is also a very important equation. So, in the region of 0 charge density, that is this region, and this equation is called Laplace's equation. Okay, so, we now have an idea about the Poisson equation and Laplace's equation. The solution of this equation we will do later. So, quickly let me write down the forms of potential in different charge distribution. So, next is the forms of different form of potential, or simply forms of potential. And what is that? So, first in case 1, we have discrete charge distribution. Charge distribution consists of say isolated point or isolated charge. So, isolated point charge are forming a charge distribution, and for that, if I want to find out the expression of the potential, what it would be, that is the, so this is suppose the coordinate system, and in this coordinate system we are having the charge distribution like this. Some random charge distributions are there like this, and say this is Q1, Q2, and this is Qk. So, I want to find out the potential at the point R due to all this charge distribution. So, for Q I can have this is R vector K and this quantity is R minus Rk. So, I can simply use the superposition principle because phi at this point P at point R is simply the superposition of all the phi's that we have for different charges. Say K tends to 1 to, if there are n charges, it should be like this. So, if I write it, it is simply 1 by 4 pi epsilon 0 and then summation of Q k divided by R minus R k, and that is all. K goes to, so this is a, so each, for each charge particle we have the potential here, and if you simply add this, we will going to get the total potential at that point. This is for discrete charge distribution. Well, what happened when we have line charge? So, this is case 2. So, case 2 I have, so for case 1 we have charge distribution with isolated charge point, and now this is simply line charge. So, I have a line charge distribution. So, line charge. So, I have again a coordinate system here and a line charge is a line is given like this. This is a dl prime and the coordinates are distributed like this. This is R, this is R prime, and this is R minus R prime. So, the point here, so my simply my phi r will be, so let me write it here. So, phi at the point R will be 1 by 4 pi epsilon 0 integration of line charge distribution lambda or the density lambda, then dl prime and R minus R prime, that is all, with a line charge integration. Next, in a similar way, if I go on in case 3 for surface charge, I have a coordinate system and then I have a small surface element here which we call ds prime, and like before we have these coordinate points. This is R prime, this is R, and this is R minus R prime. The potential here should be simply phi at R for this kind of distribution is 1 by 4 pi epsilon 0 integration of sigma, which is a surface charge density ds prime over r minus r prime, okay, over surface charge integration. And finally, the volume charge that we already discussed, but still let me write it. So, no, this is 4. So, we have a volume charge element here, like the way we find the electric field, we are now. So, here we have a volume element and its coordinates are defined the way we defined so far for all other cases, that this is r, this is r prime, and this is r minus r prime. So, the potential that one can expect at point r is simply 1 divided by 4 pi epsilon 0, then volume integral rho at r prime dv prime divided by r minus r prime, that is all. So, this is the for volume charge, this is for volume charge. Okay. So, after all this distribution, so let us now quickly do few problems. One is potential due to uniformly charged wire of length 2L, say. So, we will try to do one quick problem and try to find out the wire. So, this is the wire we are having, but this is a finite wire, say this is the z direction, and we have the wire of 2L, this length is 2L, and uniformly charged means the line charge density is lambda here. Okay. Now, the point is, what should be the thing that we want to find is what should be the potential at some point, say here at r. So, from here to here this is say r, and what should be the potential at this point. Mind it, the potential is the scalar quantity. So, if I want to find out the potential, so small element I will calculate, for all the small element I will calculate what is the potential here and then sum it over. So, let us take a small segment here, and maybe this is say dr prime, and from here to here this is r prime, and this length from here to here this is curly r, which is r minus r prime. From the geometry we can have one thing, let us first do that. So, when we integrate, so this is the 2 points of the wire, and if this angle is theta 1, so this angle has to be minus of theta 1, because I am measuring from this axis, and r prime is equal to r into tan theta, because this is r prime, this is r divided by r prime is tan theta. So, r prime equal to r tan theta. So, dr prime is sec square theta and then r d theta, and mod of r square is simply r square plus r prime square, which give us r square 1 plus tan square theta. This is nothing but r square sec square theta. You can also find it using the simple geometry what is there. It is just a I calculate because we are going to use this later on. So, now what is my phi at point r? So, this is 1 by 4 pi simply epsilon 0 and then integration, then lambda and dr prime, then mod of r minus r prime. So, that quantity is 1 by 4 pi epsilon 0 integral I need to put the boundary here, the value here. So, dr is goes from minus L to plus L, that we will put later. So, lambda dr prime, and this quantity is root over of r square plus r prime square. So, if I go on with the calculation whatever we are doing, so at point r is lambda divided by 4 pi epsilon 0, because lambda is a constant I can take it out, and dr prime we calculate here. So, that value we will going to put. It is sec hyperbolic square theta r and then d theta divided by, this is square, divided by r square, this quantity I already calculate. So, this value is r of sec theta. So, 1 sec theta simply cancel out. So, this and this will cancel out. So, eventually we get lambda divided by 4 pi epsilon 0, then integration, and also the r will cancel out. So, simply I get simple integration, and that is sec theta d theta, and we know from the standard integral this value is now I need to put theta, because theta here is minus theta 1 to plus theta 1. So, that after putting this I can put it. So, my limit is minus theta 1 to theta 2, so theta 1, minus theta 1 to theta 1. This is ln, and then it should be sec theta plus tan theta, that will be executed at minus theta 1 and theta 1. So, this, if I now go back to the real coordinates, which is r and all this. So, it is simply ln, then sec theta I calculated, it is r square plus r prime square divided by r, and tan theta also I calculated, it is 1 plus r prime divided by r, and that thing is from minus L to plus L, because now I remove my theta. So, this value if I put, so I will get my result. It is a straightforward but a bit lengthy calculation, but anyway. So, R you will get the value at lambda divided by 4 pi epsilon naught ln, and then it will be L plus root over of R square plus L square divided by minus of L plus root over of R square plus L square. So, this is the value of the potential for a charged wire having the length plus L to minus L. Okay. So, now we will going to exploit this result to find out the total electric field at some point R, that we also calculated using the Gauss's law earlier. So, that we cross verify. So, my E now, so my phi is given. So, now I calculate exploiting this phi, I am going to calculate the E. So, electric field is minus of this quantity, right. So, the electric field I can write as a minus of the potential phi, and phi is now given, but its phi is given in terms of R. So, this is a function of R. So, I can write this operator as in spherical coordinate, and that should be unit vector R del R and then phi as a function of R. Okay. So, now phi R already I calculate. So, I can write in a simpler way. So, phi R is like lambda divided by 4 pi epsilon 0 and then ln A divided by B. What is A here? A is simply L square plus R square whole to the power half plus L, and B is simply L square plus R square whole to the power half minus of L. This is my A and B. So, now if I want to find out this E, I need to make a partial derivative with respect to R to this phi. So, del phi del R comes out to be lambda divided by 4 pi epsilon 0 will constant and stay like this, and I have 1 by A and then del A del R and then minus of 1 by B and then del B del R. Now, del A del R from the expression it is easy to calculate, and that is nothing but I have 2 R here divided by 2 into R square plus L square whole to the power half. So, it is simply equal to, because for B, because this is a negative sign and the constant. So, this quantity is simply equal to del B del R. Okay. So, eventually what I find is del phi del R is lambda divided by 4 pi epsilon 0, that is there, and I can take this R divided by R square plus L square to the power half common, because both the term I will going to get that, and only I have 1 divided by root over of R square plus L square plus L and then minus 1 divided by root over of r square plus L square plus L. Sorry, this is minus L because this is 1 by B minus L. Okay, so eventually that leads to the term like lambda divided by 4 pi epsilon 0, then r divided by r square plus L square whole to the power half multiplied by minus of the, if we calculate this and this will cancel out. So, 2 L and a plus b into a minus b. So, that is a square minus b square. So, I simply have r square here. Okay. So, eventually this term is minus of lambda, then L, and then 2 pi epsilon 0. This 2 will cancel out with this 4. So, that gives me 2 here, and then we have 1 divided by r multiplied by root over of r square plus L square. So, that should be my d phi dr, and how the d phi dr is related to E? E is simply minus of d phi dr with unit vector r. So, my electric field E here is at point r due to the wire having length 2L is simply lambda L divided by 2 pi epsilon 0 and then r, and then 1 divided by L square plus r square whole to the power half and r unit vector. So, that is the value of the electric field for finite length, for a finite length of r. So, finite length of 2L of a charged wire. Now, we calculated earlier, if you remember, the electric field for infinite wire. So, for infinite wire, I have L tends to infinity, that is the condition, right. For infinite wire I can put L tends to infinity. So, if I put L tends to infinity, I will get back my old result that we have already calculated for infinite wire earlier in the class, in earlier classes. L tends to infinity, lambda unit vector r divided by 2 pi epsilon 0, 1 divided by r. So, if I take r square common, then it should be r 1 plus r square divided by L square whole to the power half. 1 L was there in the numerator. So, that I put lower side, and to make L square plus L square divided r square divided by L square. So, this quantity will be 0 if L tends to infinity. So, eventually I will get the standard result that the electric field for infinitely charged wire, infinitely extended charged wire with uniform line charge density lambda, it is 2 pi epsilon 0 and r with r unit vector. So, that is the result we already figure out. So, I just verify this figure once again, exploiting the expression of the phi that we calculate. So, phi, first we calculate the expression of the potential phi, and then from that we calculate the electric field. Okay, so, with this note, today I do not have much time to discuss. So, I like to conclude here. So, today we are going to learn that how the potential can be calculated for different cases. In today's class, I just calculate for one problem, that for a finite wire, but in the next class maybe I can go on with this calculation, and we will going to calculate what happened when we have a charged sphere and what should be the charged disk and what should be the potential for that, and this kind of calculation we will do in meticulously. So, with that note, let me conclude today's class. Thank you for your attention and see you in the next class.